Welcome back to Chem 4300. In this video, we're going to continue the topic of chemical kinetics. And now we're going to look at a couple examples that take advantage of the steady state approximation that we learned about in the previous video. And one of those cases is something called the Lindemann mechanism for gas phase reactions. And this is going to use the steady state approximation with the pre-equilibrium approximation that we also talked about in that section. Now, when you look at a lot of gas phase reactions, the reactions are often first order in the reactant A. So in this case, A, we have some rate law, it looks like this. That reaction that takes place has an overall reaction of this, but the mechanism is not as simple as A just going to a product. What has to happen for this reaction to take place is that A has to collide with something and get into some kind of excited state. And then in the excited state, it will decompose into this product or react to form the product. And that's the mechanism that we have in the Lindemann mechanism. So it has to collide with some other kind of molecule to get enough energy to do this reaction. So the way we'll describe this is that A is in the gas phase, and it will react. It will collide with another species we'll just generically call M. M could be another A molecule, or it could be some buffer gas that A is in a container with. And so it will collide with that other molecule, putting A into some excited state, and then A in the excited state will have the energy it needs to transform into the product. So when you add up these two steps, you get the overall reaction. But this reaction is a two-step process. So what we're going to do is use the steady state approximation in this approach, and we're going to say that the intermediate here, which is A in the excited state, its rate law is dt is equal to K1 times A times M, right? So the formation of this is K1 times A times M minus, of course, there's an equilibrium, so A excited state could just go right back to the unexcited A. So that's going to be minus K1 A star M. And then the possibility that it can go to the product, which will be minus K2 times A star. That's our expression for the intermediate, A star. And we're going to say in the steady state approximation that that is equal to 0. With that definition, we can solve for the steady state concentration of A star, and then we can write down the rate law for the formation of the product, which is K2 times A star from this expression here, substitute in our steady state approximation, and we get this equation for the rate of the product formation. Now, if I take that equation that I just did, make this substitution here with the steady state, what we find is that at high enough pressures, then this term in the denominator is the concentration of the molecule that it's colliding with. If there's a lot of molecules for it to collide with, then this combination of K minus 1 times M is going to be larger than this K2 term. And if that's the case, if we can eliminate that K2 term, then you can see that the M's are going to cancel, and we're going to end up with this equation here, which should look familiar from the last video. And we're going to recognize then that this reaction is going to be first order in A with a constant that's going to be given by this equilibrium constant times K2, or just K1, K2 over K minus 1. Okay. Now, the other extreme is, what if we're at really low pressures and there's not a lot of other molecules for A to collide with? Well, in that case, then this term is going to be small, and we're going to have the expression here where K2s are going to cancel, and now the rate is going to look like this, and it's going to be related to the concentration of the species that it has to collide with times the concentration of A. So this becomes, again, it's still first order in A if we lump together K1 times M, but you can see then it's going to depend on the concentration of M for that reaction. So here are the two cases we've solved with the Lindemann mechanism. If I made a plot of what you see as a function of the concentration of M, the species that it's colliding with, then say that maybe that's just like a nitrogen gas or some other inert gas that's in the reaction, then this reaction here, for example, the isomerization, you can see that at low concentrations, we have one rate, which is going to be now K1 times M. Low concentrations of the buffer gas, the gas that it's colliding with, will have one rate. And then at high concentrations, it becomes independent of this M, and then it becomes disproportional to the concentration of A, and it now looks like this. So here we see those two limiting behaviors. When the buffer gas that it's colliding with becomes the limiting factor, then it has a rate that's proportional to that concentration. But when we have more than enough buffer gas that for it to collide with, then the rate just becomes independent of that here. And then this rate would be proportional to the amount of A if I had plotted that as an axis there. Okay, so that's the Lindemann mechanism. Let's take a look at another example, is chain reaction mechanisms. And this is where you have a number of steps where intermediates are being produced and consumed. And they can be pretty complicated reactions. This is what you see for explosions and combustion and polymerization reactions. Classic example is this reaction here of just H2 reacting with bromine gas to give HBr. It looks like a simple reaction. Here's the observed rate law. You can see that it involves rates that to the Br2 to the 3/2 power. So it looks like a pretty complicated rate law, even though we have such a simple reaction. So let's look at the reaction mechanism for this and see how we can obtain this observed rate law. So the way it works is that we start out with bromine, and it has to collide with some other species, some inert species that are not necessarily inert, but it could be any species in the container that will turn this bromine into two radicals. So the bromine will collide, break apart into two bromine radicals, and leave the original species that it collided with. So the rate here is equal to some rate constant times Br2 times the concentration of whoever it is that it's colliding with, which can be, in this case, say Br2 or H2. Then we come to what's called the propagation step. So the Br radicals can react with the hydrogen to form HBr and leave you with an H radical, and that will have this rate for that step. You can also have H radical, which formed from here, say, reacting with Br2 to form HBr and leaving with a bromine radical that has this rate expression. Then you can have what are called retardation steps, where H radical reacts with HBr to take you back to H2 and Br radical. That has this step. And then finally the termination step, where Br radical reacts again with this one of these inert species, or Br2 or H2, and combines back into Br diatomic, and you give you back whatever it was that it collides with, and that has this right here. So here are all of the steps in this reaction, and now with all of these rates, we want to put together the overall rate law. All right, so let's take a look at how that comes out. So here are all the steps, and let's look at what the rate of HBr formation is going to be in this case. So here we see that for HBr, where do we see it? Well, we see it here being formed, and here being depleted, all right? So we'll start down with the first case where it's being formed here. So here's, right here, HBr being formed. So that's going to be Kp times Br radical times H2. That comes from this reaction here. And then the next case here is we're going to have it being formed here. So it's going to be Kp prime times H radical times Br2. That's this term. And then we have this step here where it's being depleted by its reacting with the hydrogen radical, and that's going to be minus Kr H radical times HBr. So what we're going to do is we're going to look at the intermediates here, which are two, the H radical and the Br radical. And we're going to write down the expression for the H radical. So again, let's look at that one here. So H radical shows up here, here, and here. So for the formation of the H radical, it's KpBr radical H2. That comes from this reaction. And then we lose the H radical here in this reaction. So that's going to be minus Kp prime H radical Br2. And then we have this case here where we lose the radical minus Kr H radical HBr. And that's one of our intermediates. We make a steady state approximation. We're going to set that equal to 0. Similarly, we have Br radical. That Br radical is going to be formed here. It's going to be consumed here, formed here, and consumed here. So every one of these are going to contribute to this rate. So I'm going to write them all down here. I'll let you check that, but essentially it's going to be all of these coming together here with the appropriate sign. And we're going to set that equal to 0 because we're going to make the steady state approximation. So we have now two equations and two unknowns. And our two unknowns are the hydrogen radical concentration and the Br radical concentration. So we'll go to the next slide, and we'll take this equation and this equation, and we are going to solve them for those two concentrations, and here's what you get. So I'll leave this again for an exercise for you to do at home. But you can see that the M, the species that involved in the collision to get you to break up the species or to cause the reactions and the various ones there, you can see here M was involved various ways. That M cancels out of that reaction, of these concentrations. And finally, when we bring it all back together let's go back to here again, go back to this equation and substitute in those steady state values here and here, we'll get this equation here. And you can look at that and look at the observed rate that I gave you earlier, and you can see that we can identify some of those rate constants. So here, these terms that we identified in terms of the elementary steps are associated with this rate constant K, and these rate constants from the elementary steps are associated with that observed rate constant K prime. Okay? So those are just two examples of how we can use the steady state approximation to solve these complicated reaction mechanisms. So we'll stop this video here, and the next we'll look at temperature dependencies of these reaction rates.